Let's talk about the Brouwer's fixed point theorem. The Dutch mathematician J. Brouwer gave us one of the most famous theorems in topology, which states that for every continuous function in a closed disk D, but honestly, let's ignore the complicated jargon for a second. I will try to state the theorem in a much simpler way. Think about stirring a cup of coffee. You're moving every particle from one place to another, creating a continuous transformation. Brouwer says that no matter how much you stir, at least one point has ended up exactly where it started. You're right, it remains fixed. Let's look at a coffee example closely. Let's assume for this example, the liquid in the cup is set into motion such that the particles on the surface remains on the surface. So every particle move around onto other positions, and at any given instant the position of the particles on the surface defines a continuous transformation of the original distribution. Each such transformation leaves at least one point fixed, meaning one point has not moved. For a simple circular rotation, it is always at the center. Now we are starting to understand Brouwer's statement mathematically. There exists at least one x which belongs to this closed domain D such that the continuous function maps it to itself because at least one point has not moved. Let's imagine a massive cyclone is tearing down towards the shore. The entire system is in constant violent motion. The air movement in the cyclone is in continuous transformation. Yet, Brouwer's fixed point theorem guarantees that even here, the center, the eye of the storm, remains perfectly still. Imagine this is a thin rubber disc, and the points of this disc are subjected to continuous transformation, in which each point remains within the disc, although differently situated. This disc might be shrunk, turned, folded, stretched, or deformed in any way, so long as the final position of each point in this disc lies within its circumference. There exists at least one point in this transformation which has not moved. But although keep in mind that the fixed point can change in time with each instant of a transformation. Now we are in a position to understand Brouwer's statement mathematically. Every continuous function f from a closed disk D to itself has at least one fixed point. There exists at least one x which belongs to the domain D such that f of x is equal to x. Now let us look at this 3D visualization. The surface here represents a continuous deformation. The color shows us the displacement, how far each point has moved from its original position. The red areas represent large movement, while the blue areas shows us where points have moved very little. Now look at that bright glowing dot. That's where the displacement is exactly 0. That's a fixed point. Notice how the displacement gets smaller as we move closer to that dot. That happens because the surface is one continuous connected piece. Because the surface cannot tear, the movement is restricted near the fixed point, forcing the surrounding area to stay closer to its original position. In other words, as a consequence of the existence of a fixed point, the surface ensures that points have lower displacement as they get closer to that spot. Look at that snapshot below. As the surface wraps, this fixed point can move, split, or merge. But no matter how much the surface deforms, Brouwer's theorem guarantees that at least one of these points where the displacement is 0 will always exist. Let me tell you something incredible that Brouwer's theorem guarantees. Imagine you lay the map of your country on the floor in your country. Because the map is a continuous representation of the country, Brouwer's theorem says that somewhere on that map there is at least one point sitting directly over the actual place it represents. If you enjoyed this video, please like, subscribe and share. The mission of this channel is to make science and math education accessible to everyone, making complex concepts easy to understand through visualizations. I'd love to keep creating content that matters to you. So if you'd like to see more videos like this, please leave a comment and share your feedback. Let's make learning easier together.